So first of all, I thank the organizers for their invitation, and I also show my gratitude to Professor Ramurthy, who always encouraged throughout my research career, still encouraging. So I am very happy that I was able to attend some part of the conference. So today's my lecture will be on some property of differential operators acting on Jacobi forms. A brief introduction of Jacobi form, then I will go to the problem. So a Jacobi form, in short I write JF, is a holomorphic function defined on H cross U. This is the upper half plane. It has two types of transformations, one with respect to the group SL to Z, so satisfying phi of A tau plus B by C tau plus D, Z by C tau plus D is C tau plus D power K e power 2 pi I MC Z square by C tau plus D into phi of tau is there. This should be true for every matrix A, B, C, D. So we will just work on gamma 0 n, a subgroup of SL to Z. And second transformation is with respect to the lattice. Phi of tau plus Z plus lambda tau plus mu is e power 2 pi I m into lambda square tau plus 2 lambda is there. Phi of tau is there. So this should be true for every lambda mu in Z2. And third one is, as usual, the holomorphic at all the curves. Phi is holomorphic at all curves of gamma 0 n. In particular, it has a Fourier expansion or the infinity given by power n zeta power r n are integers r square less than or equal to 4 n m, where here we will fix this notation. Q stands for e power 2 pi I tau. Tau is the upper half plane variable and zeta is 2 pi Z. Z is complex variable. Okay, so the space, vector space of all Jacobi forms of weight k and this index m for gamma 0 n is denoted by symbol jkm. Yeah. So this is weight index n. The space was extensively studied first by Eichler and Zagier in connection with the connection between Ziegel modular forms and elliptic modular forms, the so-called Saito-Kurokawa correspondence. So the first studied by Eichler-Zagier in 1985. So next we consider, we need some kind of differential operators. For that I need the Taylor expansion of phi belongs to jkmn. You just consider the expansion around z equal to 0. So where chi mu of tau are these functions of tau, these Taylor coefficients, and one can define a differential operators involving these Taylor coefficients the following. So for each mu, define d nu of phi to be some constant time times psi mu, and this constant is depending on k and nu, summation some constant minus 2 pi I m power mu, some k plus mu minus 2 factorial by k plus 2 mu minus 2 factorial mu factorial, and this is the derivative of chi 2 nu minus 2 mu, and then mu the derivative of chi So once you have this combination of this chi mu's, where mu 0 to the integral part of mu by 2. So then one can see that d mu phi is a modular form of weight k plus nu on n. So for each mu we have a differential operator with mapping the Jacobi forms to the space of modular forms. So I have from mu equal to 0 to m, 2m, I have 2m plus 1 differential operators. So I'll map this Jacobi forms to modular forms. So okay, I'll just make a statement, theorem, like let's say here. Note that psi 0 is, so d0 is psi 0 constant time, which is constant time chi naught, is a modular form. So each psi nu is a modular form. So I can say d nu jkn and then second is for m n greater than or equal to 1, we have d2 nu equal to 0 to m is injective mk n and direction sk plus 2 nu equal to 1 to m. Note that though we have differential operators for mu equal to 0 to 2m, whenever we take odd, since k is even, it will be mapping is trivial to 0. So whenever k is even, only the even indexed operators will exist. So therefore, there are m plus 1 differential operators acting on Jm, whose direction is injective. This is already known. So next one is the study of the kernel. So study of kernel D naught. So this was undertaken by Arakawa and Booker. Then they studied in two of their papers. One appeared in 99 and appeared in 2003 is in Crille, and this is the Hamburg Journal, where they studied the kernel of this map D naught and then showed that this information of the kernel gives rise to some applications, especially on the conjecture of Hashimoto, which is on the linear combination of theta series arising from certain quaternion algebras. Okay. So also it is known that D naught is not injective when k is, so it is known D naught is not injective in general when k is greater than or equal to 4. So the only special case of injectivity one can think of k equal to 2. So the interesting case, so the injectivity of this also was studied by Kramer in 1986. So first I will just explain what is the work of Arakawa and Booker, and then I will come to a conjecture made by Booker. So the work of Arakawa and Booker, I just read, in short I write AB. So this is, so what they have considered, you take the index one case, you take jk1 and n, and then we have the d naught naught and take the kernel of d naught on this as, on this space as jk1 0. So that is the kernel. So any phi, we have phi belongs to, this implies d naught phi is 0. It is nothing but phi of tau comma 0 is 0. By using this observation, they gave a mapping. They found a modular form whose weight is k minus 1 and the level is n with some character w. So from there you can just give a mapping phi goes to phi coming out of this form. They also gave applied the next differential operator d2 on this and then it got an isomorphism to sk plus 2 n. This will be going to be a subspace of this because you are mapping from the kernel, so you do not write 0. So therefore naturally there is an isomorphism from the bottom which sending phi to a function d2 phi which is given by phi times some modular form psi. It happens to be the psi is a multiple of eta power 6, constant time eta power 6 tau, where eta is the Dedekind eta function. Okay, so now I will mention the theorem of Arakawa Booker, which talks about subspaces of the cusp forms having this kind of divisibility property. So theorem, so let sk eta of n be the subspace of all forms belonging to skn such that f is divisible by eta power 2k minus 2. So then they show that if n is 1, then this skn eta becomes trivial if the weight is not multiple of 12 or if n is pair free, then the same property is true, sk eta of n is 0 whenever k is congruent to 4 or 10 modulo 12. So this result we will be using later. So now look at this case there. Now when I take k equal to 2, I come to, sorry, this k and that k don't get confused. Now here k equal to 2 is the case. Okay, k equal to 2. What I have here is I have jk1 n and then I am ending into the space S4 of n, where this form d2 phi is a multiple of eta power 6 and 6 is given by 2 into k minus 2. So 6 is 2 into 4 minus 2. Therefore, the property here is satisfied and your weight is 4, therefore weight is 4 modulo 12 and it is divisible by 2k minus 2. Therefore, this space, particular space becomes 0 when k equal to 2. So this is what the application of this particular theorem in this situation when k equal to 2 gives you that injectivity of d naught. So this was the work by Booker, Arakawa and Booker, and then when he also he observed that similar thing should happen in higher index. So not only m equal to 1, it should be true in general case also. So I'll just mention the conjecture in a more general setup. So I'll just say hypothesis. From there you will just derive a conjecture and then we'll show that. So we have these operators. So I have d0, d2, I have do t nu. You just remove this is jkn injective to mkn sk plus 2 sk plus mu equal to 2 sk plus 2 nu sk plus 2m So we know that if I take the whole set of m plus 1 differential operators, it is injective, which is known. Now question is that can one remove one of these operators and still retain the injectivity? So we call this hypothesis as I 2 nu k m n. So this is called, whenever I say that I 2 nu k m n, that means I can remove the mute part of this decomposition and correspondingly delete this space here. Still we retain the injectivity of these operators. So the conjecture is that, conjecture due to Booker is, so and then we denote by when mu equal to m, we drop this 2 nu, so we write I k m n. That means I can remove the last operator, still I get the injectivity. So I 2 m n is true for all m greater than or equal to 1. So this is the conjecture which we will be talking about today. So already we know that when m equal to 1, the result of Arakawa and Booker gives the conjecture when m equal to 1. So in my earlier work with Karamdev, we have extended this method to the index equal to 2 case, exactly following the work of Arakawa and Booker. So I will just correspondingly I will write jk2, I have to take 2n, you have 2n, I have 2n here, and before we proceed, I think we need some more information. So for each phi, I can write in terms of the theta decomposition, I can write, so h mu of tau, theta m mu j of tau is a, where mu is 0 to 2m, where this theta m mu j of tau is nothing but q power r square by 4m theta power r. Something is missing, I will just the particular one. Yeah, and h mu tau is sigma cnr q power n minus r square by 4m. N are integers, r is congruent to mu modulo 2m. So this is, so from this I get some vector valued modular form, and also this vector is also a mod vector valued modular form. So we have this, the vector theta m is given by theta m mu equal to 0 to 2m. If I take the transpose, we call the column vector. Then it satisfies this transformation, theta m of a tau plus b by c tau plus d, z by c tau plus d is c tau plus d power half, e power 2 pi I m, c z square by c tau plus d. This is coming from the this transformation of phi, and then I have some projective representation um on result to z times theta m of tau z, where u2m c is a projective representation, and the h also satisfies, the h vector also satisfies and this is a row vector. I just consider H is H naught etc. H 2m. It satisfies C tau plus D over k minus half H tau u m gamma bar transpose. This is satisfied for every gamma A, B, C, D. Whatever group you take, and it is satisfied by this. Okay, so now you use this one for any phi. I have the theta decomposition. So we have phi, I have H naught, theta naught, I have H1 and H3 equal, so theta 1 plus H2 theta 2. So when I have the D naught acting on this, so phi of tau 0 equal to 0 gives rise to two functions. One is phi naught, which is given by H naught by theta 1, and phi 2 is minus H2 by theta 1. This theta 1 is nothing but theta m comma 2 comma 1 of tau 0. So theta nu is nothing but theta m nu of tau 0. So when I apply the D naught, these are theta constants. So I have two forms, and then using the transformation property of phi, one can show that this pair is a vector valued modular form. Phi naught phi 2 is a vector valued modular form. So therefore, so in a corresponding way, I can map phi D naught phi equal to 0 gives phi 0 phi 2 transpose, and which is belonging to this space, again m k minus 1 level 2n and with some character, and then again apply d2 to this. So therefore in this case d2 phi is given by phi 0 psi 0 plus phi 2 psi 2. There is again a vector psi naught psi 2, a vector valued modular form whose product of this one gives this d2 phi. So therefore we can prove such a diagram in the case of some, because we can use it because of some special properties of the representation um appearing in the theta transformations. So now in this setup we have three operators d0, d2 and d4. So now we can show that d0 directs some d2 injective. Using this data, if I take any phi in this kernel of this num, one can conclude that this phi will become 0. Therefore, in this case when m equal to 2, one can drop the operator d4. So therefore the conjecture is true for m equal to 2 by exactly following this Arakawa and Booker's method. So now come to the work which I have recently done with Soumya Das. So I'll just state the theorem and then we'll see a brief sketch of the proof or method. The proof, now I think we are following a different method to attack this problem, and then we solve the conjecture, and moreover we get a more general results, not necessarily when k equal to 2, for k greater than 2 also we get some injective results. Okay. Okay. So first I will statement theorem. The previous one was whatever I explained, the n equal to 2 case was with Karamdev. So k greater than or equal to 2, be an even integer, then the property k m n, that means still I have, I have this I k m n means I am removing the last operator. So I'll just so this is called the IKMN. That means I can remove the last one is true for k equal to m equal to 2 and all square free n. So though this is the case, the previous case which I explained now, we can give a different proof. Instead of using this isomorphism, one can directly prove this statement. The second and third are more general things. The same property holds for all n greater than or equal to 1, provided the difference n minus k is greater than or equal to 1. Sorry. When n is square free, here notice that there is no condition on n, square free condition. So this is true for every n. So when I restrict n square free, I can gain more on these values. Is true for all n square free, provided n is odd and this difference is greater than or equal to minus 1. So in particular we get the result of Arakawa and Booker when k equal to 2 and m equal to 1. So when I put m equal to 1, I can put k equal to 2, still I get this true. And finally, if it's true for n equal to 1, m is 1 3 mod 4, that is m odd and the same condition. So you will see that why these conditions are coming in the moment and when you sketch the proof. Probably I will just use this also because I need this and that, and then the remaining space I will use it for giving a sketch of the proof. Sorry. So now we already saw that phi of tau is this Taylor expansion. So from this we see that chi 2 nu is, and then use the decomposition. Some constant time, so I will just do, then from this implies h mu. I can, these are all the derivatives at z equal to 0, I can transform to the derivatives with respect to tau, which we call as theta m mu of nu, nth derivative, and then with respect to tau. So this I have 0 to m. Now therefore, I have a system of equations, there will be m plus 1 system of equations. You put it in the matrix form, I have theta m0, theta mm, theta m0 derivative, theta mm derivative, theta m0 mth derivative, mth derivative, apply to, I just put this one as some hm prime. This is nothing but h mu times this constant is given by this vector chi 0, chi 1, chi m. Okay, so this matrix we divide by this capital Wm, and it is known that this determinant is eta product, so eta power. Okay, so note is a round scale determinant, so determinant of is denoted by the script Wm is nothing but constant time eta power m plus 1 into 2m minus 1. Therefore, by inverting this matrix, what we have, I can write h in terms of the, and now comes to the, assume that where phi belongs to the intersection of kernel do nu 0 to 2m minus 2. So 0 to m minus 1. So I have 2 nu. Assume that I remove the last part and then I am in the kernel. So phi belongs to the kernel gives you the information that chi 2 nu is 0 for all nu equal to 0 to m minus 1. So this gives you all these chi zeros up to chi m minus 1 will become 0 because of the assumption that your phi belongs to the kernel of all these operators from 1 to 0 to 2m minus 1. Therefore, I can express this in terms of the inverse of the matrix times this, which gives rise to, this implies for each phi in the intersection of kernel, what we have is this h mu's, I am just omitting the prime, so up to some constant is given by some constant time chi 2m into omega mu by this determinant. This script wm determinant is there. So this is nothing but now omega 0 omega m transpose is the last column of the inverse of the matrix, inverse of this matrix wm. So if you invert and I just denote the last column by this w0 wm, then I can express this. So this is the basic ingredient. I can just remove this. So I will just go to the general proof. The other one, this case is, one can easily do that straightforward. Now anyway, I will just go to the general case. So what we have is h mu by this, I bring it to this side. So I have so what we do is that multiply both sides by some. So I have to show that, you will note that this is this wm is, what is the eta power? Where did I write eta? So that I removed it. So is constant time eta power. So this gives the divisibility whatever required in this result. So we already know that this is divisible by this eta power. So consider, so multiply by a modular form of weight s in level n, and then what we have is some constant time chi 2m h by eta power beta is h mu h by omega mu eta power beta minus lambda. So this technical details please excuse. So lambda is some the order m plus 1 into 2m minus 1, beta is 2 into 2m plus k plus 2s minus 2, alpha is m minus 1 into 2m minus 1. So these are the things which we will set. So now using that we define psi to be your h mu into h by omega mu into eta power beta minus lambda. So one more parameter r we introduce, and then you define phi to be eta power 1 minus 2 r psi, and then show that this phi is a modular form. So first of all note that whatever the vector you just define this omega m defined to be the vector, this one of the main ingredients is to show that this is a vector valued modular form with some multiplier system. So that's an important key ingredient in this. Using that, and using the fact that these h and h mu vectors are modular forms, one can show that this phi is a modular form of weight 1 minus 2r on gamma 0 n. So that is the basic thing. Then we will go to the cases. So naturally, whenever r is greater than 2, this will become negative weight. Therefore, something is wrong, I think, eta power eta minus r, sorry. Eta power minus r, then it is a modular form of weight 1 minus r by 2. So this is a weight 1 form, and then multiplying by eta power minus r gives you 1 minus r by 2. Therefore, whenever r is greater than 2, this will have a negative weight, therefore this phi will become 0. Therefore, when phi becomes 0, psi is 0, therefore your h2m will become 0. So that is the contradiction you will get. So now one by one we will just derive it. I think another 5 minutes. Okay. So now take case n greater than or equal to 1. Now choose r greater than 2, and then I don't want, in that case I don't want this h, I can take h to be some constant, so s is to be 0. Then this gives a contradiction, since this implies phi is modular of negative weight, implies chi 2m is 0. So therefore we get a contradiction, because that is the only vector which was non-zero. Therefore when chi 2m also 0 means the whole function Jacobi form will become 0. Therefore that phi will become 0. This implies, therefore that proves the injectivity in this case. Now next case is that when n equal to 1, when n is square free, so we make use of this theorem, and the basic thing is now choose s to be equal to m minus k plus 1, which is greater than or equal to 0, and then note that, and then assume that h is a non-zero modular form, and because of these relations what we get, this congruence condition leads to, this congruence condition leads to 2m plus k plus s congruent to 4 comma 10 modulo 12. We substitute the value of here, what we get is m is congruent to 1 or 3 modulo 4, and also from here I can get the condition m of power k greater than or equal to 1 minus 1. So I need m r and m minus k greater than or equal to minus 1, and this is this case. I also need the n square free case, because n square free only I can use this one. So this takes care of this. The one which I took the previous case, n greater than or equal to 1 or greater than 2, that case is given by this. And finally the same one for this also one can make, for which I think we have to use this condition. The weight is not divisible by 12, is not 0 modulo 12. So if we combine all these things, what we get is this result. Note that not only when k equal to 2, for a k greater than 2 also one can get the injectivity, and also in some cases this n square free condition is not needed. So this is a much improved result, not only proving this one, and a much more general result is also proved. And in the case of, can one remove the other operators, there are some examples in which case we may not expect the injectivity. I'll just give one example. So in the case of m equal to 1, take p equal to 3, level 3, I have J21P, weight 2 and index 1 form, and this is non-empty. So there are non-zero Jacobi forms, and we know that this J21P is isomorphic to the weight 3 by 2 plus space of level 4p, and your D2 map takes this to S4 of p. So D2 takes J2 1 to 2 plus 2, so that is weight 4 cusp form, and we know that this is 0. Okay, so therefore I cannot remove, this is not an injective map. So we cannot remove D0 to get D2 injective. So therefore the question of removing any other operator is not an easy question, so it will be very difficult or may not be possible to remove any of the middle operators. So what our result says that one can always remove the last operator to get the injectivity of the differential operators. Thank you very much.